Well, good morning, physics folk. We are starting to enter the home stretch. It will not be too long until you will be graduating and we will be bidding farewell to each other. Our last few weeks in Physics 2, we are going to look at some other applications of dynamics, starting off with the basics of flight. And this week, while I'm out, you are going to be building a kite as a way of showing your understanding of the basic flight equations. So let's start talking about all that kind of stuff right now. Okay, so here's what we're going to do. First thing I want to do is I want to derive the basic flight equation so you get an idea of just how lift depends on things like the surface area of a wing or the surface area of a kite, and also how it might depend on the velocity and some other characteristics. So let's see how this works. It does all come about from F equals ma, but I do have to tell you there's nothing really truly intuitive about how the equation is developed. Just I happen to know it from experience, and this is the classic way of developing the equation. But if it seems to you like a bit roundabout, or you aren't quite sure why in the world we would do it this way, just keep in mind that's usually how it is the first time you learn something in physics. Sometimes even the fourth, fifth, 10th time you learn something in physics, you're not quite sure why they did it that way. But you know, with the benefit of decades of hindsight, then you start to see, oh yeah, I guess that makes sense to do it that way. So, so suspend some disbelief, and hopefully you will understand a little bit more by the end of the unit. What I'm going to do is I'm going to derive an equation for lift, basically a way of calculating how fast the air has to be moving for something to take flight. Now that can be the air moving into a kite, because kites are typically stationary, or it could also be a plane moving into the air. So the speed's going to be the same no matter how you look at it. So let's get started. We're going to go back to F equals ma, or F equals mass times the change in velocity per time. You can see I blew that up just a little bit over here. So F equals m times change in velocity per time, but I'm actually going to pull out the change in velocity outside, and I'm going to make this mass per time. And I'm going to define a brand new quantity, something that's called mass flow, or MF. And that is mass per time. You can think of that sometimes as, like, if you were talking about water flow, it might be in gallons per minute, but mass flow is going to be in kilograms per minute or kilograms per second in this case, and we're talking specifically about air flowing. Okay, so it's the amount of mass of air that's going to flow per unit time. You can think of it in kilograms per second. We're not going to worry about the units right now. And we need to bring in a couple of other ideas. Remember what density is all about. Now, density is represented by the letter rho. It's Greek letter rho, and it's mass per volume. This is a little tricky. Don't confuse velocity, little v, with volume, big V. Now, we happen to know that density is mass per volume, therefore mass equals density times volume. So we can also write the mass flow as mass per time, which is density times volume from there per time. Okay, now we're going to start to think in terms of proportions. You know that velocity of a cube would be equal to x cubed. That's length times width times height. But it actually wouldn't matter if it's cube or not. The proportions are going to be the same. It's going to be length times width times height. So that can be a prism, parallelepiped, you know, whatever has units that are cubic for volume. We're just going to pretend it's x cubed because that makes things a little bit easier, but works out to be the same no matter what. Now we can say that the mass flow, still mass per time, still rho volume over t, but I'm plugging in for volume x cubed, and I got rho times x cubed per t, or rho x cubed over t. I'm going to make this a little bit strange. I'm going to pull a fast one on you here. Since mass flow we now know is rho x cubed per t, I am going to take x cubed and make it x squared times x. There's no reason to think, why would I do that, right? Well, you'll see why in a second here. Rho x squared times x per t. X over t is also distance over time, which is velocity, and x squared is area. Right away, we start to see how the area is going to matter. We don't have to think about the volume of a wing. We're just going to think about the area of the wing. And x over t is the velocity. So now we have a different expression for mass flow. It is rho times area times velocity. A good bit simpler, and we don't have to think about the actual mass. We don't have to think about the actual time. Kind of a really smart thing if you think about it. Okay, so imagine air hitting an airfoil. Now, I drew in a theta right there. That theta is going to be to represent the fact that the angle is clearly important. So wind or air will hit the airfoil or the kite area, however you want to think about it, and it's going to bounce off. You're going to get some deflected air, and then by Newton's third law, the reaction force is going to produce the lift. And the lift gets made easier by the fact that you've got an angle in there, because above the airfoil, you've got less air per cubic meter, which means that there's lower pressure. So the deflection is going to be related to the angle and the velocity. You can see clearly there's a point at which the angle becomes too great and then the air resistance is dramatic. Typically, that angle seems to be in practice somewhere in the neighborhood of 7 degrees, but don't worry about that for right now because that's all determined experimentally. Just a little bit of air visualization for you here. You notice that the air is moving over the wing faster than it is moving under the wing, and that gives us a region of lower pressure on top. Higher velocity, lower pressure, because the air molecules are in contact less frequently than they are on the bottom. This is sometimes embodied as the Bernoulli principle. We're not going to get into the full guts of the Bernoulli principle or the equation quite yet. It's the foundation of fluid dynamics. But with an increase in speed of fluid flow, and that can be water, that can be air, any kind of fluid, comes a decrease in the pressure of the fluid. So once again, back here, higher velocity, lower pressure on top of the wing. Also shown right here, higher velocity, lower pressure on top of the wing. Same sort of thing there in these GIFs. You can see that it not only applies to an airfoil cross-section of an airplane wing, but it also applies to something like a baseball. So those of you who, if you play baseball, you know that there's a certain way you can throw the ball where you can take advantage of that idea. A couple of other expressions or a couple of other GIFs to show you right here. Again, the pressure on top is lower than the pressure below, and that helps create lift. Okay, so let's get back to the calculation. Once again, we started off with F equals ma, or F equals m times change in velocity per time, and we ended up with that slightly different expression for mass flow rate. But the other thing I did was, we can also say that mass flow rate was, if you remember, it was rho times area times velocity. However, mass actually is going to be equal to rho times area times velocity times t. Now, what did I do there? It's not super, I didn't actually write it in here as I probably should have, but mass flow is m over t. So I basically just went back from mass flow equaling m over t, and I multiplied both sides by t. Well, there it is. Okay, mass flow is rho area times velocity. Again, density times area of wing times velocity of air. And again, mass flow is equal to mass per time. So, mass, density, area, velocity times t, F equals ma. We can also say then F is equal to m, which is density, area, velocity times velocity times theta, and all that divided by time. Okay, so I pulled a fast one on you there. What about theta? We know from experiment that the actual amount of velocity that's going to matter is related to the angle, and we keep the angle small enough. So you can almost think about it as the component of the angle. Probably the cosine component is the easiest way to think about it. It gets a little tricky, but anyway, the amount of air that is practically hitting it, the velocity of the air that practically hits the wing, is related to the angle of inclination of either the kite or a plane wing. So what do we got here? We got density. That's something you can look up for air, times the area of the wing, times the velocity squared. You can see here how velocity times velocity is going to give you velocity squared. The times cancel out, and then I'm left with times a constant. So in practice, lift is approximately equal to 0.3 times density times area times velocity squared. The 0.3 again comes about from experiment, and the velocity squared, pretty critical to see that. So, sorry, I had to take a break there for a second. So the lift is equal to 0.3 times the density of the air times the area of the wing times the velocity squared. So a couple things to notice there. That's the area of the full wing. That's the cross-sectional area that cuts into the air of the full wing. If you have two wings, it is, of course, both wings added together and the body, essentially. The velocity squared. Notice that small changes in velocity are going to produce larger changes in lift. Imagine you taking your air kind of as you're driving, maybe you're a passenger in a car, and you put your hand out the window and you start to tilt it a little bit. You can start to see just how, or you can imagine just how your hand is going to kind of take off with the increase in speed. So the lift equation is basically this. Lift is approximately equal to 0.3 times density of air times the area, the cross-sectional area, times the velocity squared. Now, for something to fly, then the lift has to be equal to the weight. In other words, lift has to be equal to m times g. So in principle, you can determine the area of the wings needed to fly at a particular velocity based on the weight of an object. So let's do that. Imagine you want to fly as a human being, flying at 5 meters per second, which is just over 10 miles per hour. And you're an 80-kilogram person. You got 80 kilograms times 9.8 meters per second squared, and you set that equal to 0.3, 1.225 kilograms per cubic meter, that's the density of air, times the area, times 5 squared. That works out to be 85 square meters. So for comparison's sake, a garage door is about 20 square meters. Is it any wonder that we're just not quite set up to fly? So now, if you have a cross-sectional area of about 1 square meter, which is kind of generous and not really appropriate, drag coefficient here, but then that would mean you'd have to be flying at about 46 meters per second in order to actually generate enough lift to soar. And not super practical because the coefficient of drag of a human being is, well, you're just not set up to fly, basically. But in any case, that gives you an idea that you'd have to be moving well over 100 miles per hour. Now, you've probably seen people in wingsuits before or hang gliders, and there you can actually practically fly. Let's talk briefly about something called wing load. Wing load is defined as the weight per area, and you can compare the weight of a flying thing to its wing load on a graph. And as it turns out, the relationship is nearly linear on a log scale. So you can also, if you like, you can graph flying weight versus velocity. Now it's kind of hard to see this. It's really sort of worthwhile to look at how the weight actually changes as a function of the cruising speed. So, or if you graph weight or versus cruising speed, or for that matter, you can graph weight versus the wing load. I encourage you to take a stronger look at this in the notes. Also, do note that it is a logarithmic scale. It's changing by orders of magnitude of each segment you go up vertically, and then it's different, slightly different logarithmically down below. So what are you going to be doing? You're going to be building a kite. The kite expression is pretty similar. It's going to be 1/2 times something called the lift coefficient times the area times density squared. I'm sorry, times density times velocity squared. Now, angle is going to be an angle of attack. You're going to need to assess that. The span is going to be the length across. You'll need to know that's your widest width across. And the aspect ratio is equal to the span squared. So again, that's a rough picture of a kite right there. You'll have to measure the area. You'll have to approximate the angle. If you can't approximate it by taking video and or picture and then approximating it, I'll give you an angle to think about. And the span squared divided by the area gives you something called the aspect ratio. So to calculate the lift coefficient, we have to have two factors. One is called the shape or inclination effect, and that is the CIO, and that's equal to 2 times pi times theta. Now that theta should be in radians. So whatever your angle is, 10, 7, 8 degrees, whatever, convert it to radians. And then there's something, due to pressure differences, we have something called a downwash effect. So the effective or corrected lift coefficient is equal to the above CIO divided by the quantity 1 plus another quantity, CIO over pi times the aspect ratio. A little hard to say that, but hopefully you can read that in the equation. And that's going to give you a corrected lift coefficient for the kite. So, using the corrected lift coefficient, the lift should be equal to 1/2 times the corrected lift coefficient times the area times the density of the air times the velocity squared. And you should find that the minimum velocity to make your kite fly is going to be given by the weight of the kite being equal to that expression for lift of a kite. So that's what you got. That's what you're going to try and show. You should end up getting velocities that are pretty small. Expect them to be under 10 miles per hour, for example. You can take a look at some kite ideas online, and I want you to keep it to 2 dimensions. Don't try building any box kites for now. Our rods will be provided, so will ripstop nylon. Hope you have a good time with this, and we will talk when I get back. Make sure you take video of any flying.